A magnet is a great tool for figuring out the direction of a magnetic field. The magnet will align with the magnetic field. That's a compass. We can also figure out direction of a magnetic field, though, by watching moving charges and how they move, how their motion is affected, or what forces are acting on them, the directions of those forces anyway. So we need to get a little bit of practice with that. That's learning target 144, determining the direction of the magnetic field based on the motion of a charge and the force that it experiences. So we're still going to be using our right hand rule. Don't get that confused with the left hand. So the right hand rule here. Keep in mind that your pointer finger is going to point in the direction of the velocity vector. Your middle finger will point in the direction of the magnetic field, and then your thumb points in the direction of the force that's acting on that. So earlier we were doing the pointer finger and then the middle finger, and then our thumb was our answer. Our thumb was our force. But in this case, we're going to have both the velocity, that's the index finger, and the magnetic field, that'll be the thumb. And so our middle finger is going to point in the direction of our answer here. So let's take a look at a couple examples of these. So first off, on number 1, we have a positive charge that's moving to the right. So with your right hand, point your finger, your index finger, in the right hand direction. Our force is shown as coming out of the board. Remember, that's the point of the arrow coming out at us. So with your thumb, that's the force finger, that needs to point out of the board or out of your screen. So you have to rotate your hand. Keep your pointer going to the right like this. Your thumb then has to rotate so it's pointing out of the screen. And then your middle finger is going to point in the direction of the magnetic field. So in this case, the magnetic field is upward. There we go. On this one, on 2 and 3, I've thrown a little bit of a change up here. We have negative charges. So negative charges, they just flip the direction of the force. So if a positive charge would feel a force this way, a negative charge feels a force in this direction. So at some point we need to flip one of these vectors. So either the force vector will think, okay, well the negative charge feels a force this way, so a positive charge would feel a force this way. Or we can just wait till we get to the very end and change our B vector, our magnetic field vector, which is how I'm going to set this one up. So we start the same way. We point our our index finger in the direction of the velocity vector, which in this case is downward. And our thumb points in the direction of the force vector. So we have something like this. So the magnetic field, if this were a positive charge, would be coming straight out of the board, but since it's a negative charge, it must be in the opposite direction. It must be into the board. So the magnetic field here, we would draw that as the circle with the X. That's the feathers of the arrow going away from us. One more time with number 3. Again, this is a negative charge, so we need to change our direction, flip our direction around 180 degrees once we get an answer. Our velocity vector this time is pointing into the board. We can see the feathers of the arrow here. A little bigger. There we go. So point your index finger for the velocity vector. Point that into the board. And then our thumb needs to point in the direction of the force, so that'll be upwards. So you're making your little gun here, and it's pointing toward the screen. And then our magnetic field vector, that's going to point to the left, but that would be for a positive force, for a positive charge. So instead, it must point to the right. So the magnetic field must go to the right. Now, if it doesn't throw you off too much, when you have a negative charge, you can also solve these problems just by, having a mirror image of your hand. So instead of a right-hand rule, use a left-hand rule. The rules are the same. We just point our index finger in the direction of the velocity vector. The middle finger will go in the direction of the B field, the magnetic field, and the thumb goes in the direction of the force. So if we do that, we don't have to make any changes for direction because your symmetrical hands, or your mirror image hands, make that change for you. So here I'd have my velocity vector pointing downward. My force vector needs to point in this way, so that'd be something like this. And then my magnetic field vector, you can, it's hidden by my hand here, but my magnetic field vector is pointing into the board, which is the same result we got earlier. Now, it's definitely worth noting here that our force and the velocity, they're always perpendicular to each other. In fact, all three of these vectors are perpendicular in the examples that we've drawn, but the force and the velocity, because of the way that the right-hand rule works, those always have to be perpendicular to each other. These two don't necessarily have to be perpendicular to each other, but the force has to be perpendicular to each of these vectors, to V and to B. Now, I mentioned that it's perpendicular to the velocity because that means that, well, if we have our object moving in this direction, velocity, and our force is, say, in this direction, perpendicular to it, force, if we wanted to find the work done by the magnetic field, we do the force vector times the distance vector, which would be in some direction this way, and then times the cosine of the angle between them. That's going to be a 90-degree angle, so that will always be 0. So the work by the magnetic field, by the B field, is always 0 for every situation. What that means is that the magnetic field, it's not going to cause these charges to speed up or to slow down. It only makes them change direction. So they're not gaining or losing kinetic energy for their motion. They're only changing direction.